Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It's our fourth and last lesson on the last topic of Form 4, which is called electronics. As usual, let me commence by giving the quote of the day, which states that take the risk or lose the chance. We shall discuss that quote at the end of our class today. So today we are looking at applications of junction diodes in rectification, and we are going to start by defining what we mean by the word rectification. So in physics or in electronics, rectification is simply the process of converting alternating current, or what we are calling the AC current, into direct current, or what we are calling the DC current. So the device used to do rectification process, we call it a rectifier. So rectification of alternating current is done by using rectifier circuits in which PN junction diodes are usually connected. So a PN junction diode is suitable for use as a rectifier because it offers high resistance to the flow of current when reverse biased and low resistance when forward biased. So this allows current to flow in one direction only when it is forward biased, hence producing what we call the direct current, or what we are calling the DC current. Then we have two types of rectification. One, we have what we call the half-wave rectification, and two, we have what we call the full-wave rectification. Next, we look at the first type of rectification, which is called the half-wave rectification. So the half-wave rectification is achieved by connecting a single diode in series with the load. Of course, this is our single diode. Then this is what we are calling our resistor load. So the transformer is used to step down the input voltage. Of course, our input voltage is the alternating current. Then of course, this is a step down transformer because it has more number of turns in the primary coil as opposed to the fewer number of turns in the secondary coil. So during the first half cycle, or what we are calling the positive half cycle, the diode is forward biased. Therefore, it conducts electricity. Therefore, it allows a free flow of electrical current. So during the first half cycle, the point A is positive. Therefore, the current will flow from point A through the diode, which is forward biased, through point C, through our resistor load, through point D, back to the point B. So during the first half cycle, or the positive half cycle, the diode is forward biased, therefore it conducts electricity. The current flows through the resistor load, or the current flows from point A through the forward biased diode, through point C, through the resistor load, through point D, back to the point B. So the current flows through the resistor load, building a voltage across it, which then decreases to zero as the first half cycle comes to an end. So during the first half cycle, the current is going to flow through the resistor load, building the voltage, that is building a voltage across that particular resistor load, which then decreases to zero as the first half cycle comes to an end. So that is why during the first half cycle, you can see there is a voltage which is being built across this particular resistor load. Now, during the second half cycle, or what we are calling the negative half cycle, the diode is reverse biased, and so it does not conduct any electricity. Therefore, we do not expect any voltage to build across this particular resistor load, that is during the second half cycle. So during the second half cycle, or what we are calling the negative half cycle, of course the current is going to flow in the anti-clockwise direction as indicated by this particular arrow. So the current is expected to flow from point B, which will be made positive, through point D, through the resistor load. However, when the current gets to point C and through the diode, it finds that the diode is actually reverse biased because the current is flowing from BD through RL through point C. However, when it gets to our diode, it finds that this particular diode is reverse biased because the point B, which is positive in the second half cycle, is connected to the N-type region of this particular diode. Therefore, it is reverse biased, and therefore the diode is going to offer very high resistance to the flow of electrical current. So because the current does not flow through this particular diode, which is reverse biased, it simply means that no electrical current is going to flow through the circuit during the second half cycle, and therefore no voltage is going to build across this particular resistor load, that is during the second half cycle or the negative half cycle. So the second half cycle, the negative half cycle, the diode is reverse biased, and so it does not. Therefore, it does not conduct electricity, and therefore there is no voltage which is going to be built around this particular resistor load during the second half cycle. So the voltage output for the half-wave rectification when a cathode ray oscilloscope is connected across the points A and B will be indicated this way. So you can see this voltage against time, of course, in seconds. So these half cycles actually represent the that is the first half cycle, or what we are calling the positive half cycle. Now during the second half cycle, the diode is reverse biased, and therefore there is no voltage which is going to build, and that is why there is a gap at this particular point. Then during the first half cycle, there is voltage which is going to build across the resistor load. During the second half cycle, there is no voltage which is going to be built. Therefore, the diode is reverse biased, and therefore that is why there is a gap. During the first half cycle, again, there is voltage which is being built. During the second half cycle, no voltage is built because the diode is reverse biased. Now, the disadvantages of half-wave rectification using a junction diode are: 1, the output, that is, the output in this rectification is not smooth because there is a phase which is being lost during the second half cycle. The second disadvantage is that there is much power loss as one of the half cycles is eliminated, because the second cycle is actually eliminated, whereas only the first half cycle is retained, because during the first half cycle the diode is forward biased, whereas during the second half cycle the diode is reverse biased. So this diode is going to help us to achieve what we call direct current. Remember, initially it was alternating current, but the output voltage will actually be what we call the direct current. Next, we look at the second and the last type of rectification called full wave rectification. So full wave rectification can be done in two ways: 1, using 2 diodes and a center tap transformer; then 2, using 4 diodes, or what we call the bridge rectifier. So we start by discussing the first way, which is full wave rectification using 2 diodes and a center tapped transformer. So you can see these are our 2 diodes, D1 and D2. Then of course this is what we are calling our center tapped transformer. So the 2 diodes are connected in such a way that each conducts a current through the resistor, that is the resistor load, during a particular half cycle as shown in the diagram below. So during the first half cycle, the diode D1 is forward biased, whereas the diode D2 is reverse biased. Hence, the current flows from point A through the diode D1 through point B, through the resistor load RL, through the point C, then of course back to the starting point, which was point A. So during the first half cycle, of course, point A is positively, that is, point A is positive. Therefore, the current will flow from point A through the diode D1, which is actually forward biased. Then, of course, through the junction, which is the point B. When the current gets to point B, it cannot use the lower router because the diode D2 is reverse biased, and therefore it will resist the flow of current through it. Therefore, the current flows from point A through the diode D1, which is forward biased, through point B, then through the resistor load RL, then of course through point C, then back to the starting point, which was our point A. Therefore, the direction of flow of current is from point A, then to the diode D1, then point B, then resistor load RL through point C, then back to the starting point, which was point A. Now, during the next half cycle, the diode D2 is now forward biased, whereas the diode D1 is reverse biased, and the path of current or flow, of course, changes. So during the next half cycle, point D is positive, therefore the current flows from point D, then through that is the diode D2, which of course is forward biased, then of course through point B. When the current gets to point B, it cannot use the upper route because it will meet the diode D1, which is now reverse biased. Therefore, the only direction that the current will flow through is through this particular route, that is through RL, then point C back to the point D. Therefore, during the next half cycle, the diode D2 is forward biased, whereas D1 is reverse biased. Therefore, the path of the current is from point D through the diode D2, then through point B, through the resistor load RL, through point C, then back to the starting point, which was our point D. So the direction of flow of current is from D, D2, B, RL, C, then of course back to the starting point, which was the point D. Then the current flows through the resistor, that is the resistor load RL, in the same direction, that is in both cycles. So the output voltage signal is as shown in the graph. So this is the voltage, then of course this is the against time. So you can see, unlike in half-wave rectification, whereby one of the cycles was getting lost, in full-wave rectification, both cycles are retained. So you can see this is the cycle for that is for the first half cycle. Then of course this is what we are calling the next half cycle. Then of course back to the first half cycle, then to the next half cycle. So unlike in half-wave rectification, whereby power was getting lost because one of the phases was getting eliminated, or one of the cycles was getting eliminated, in full-wave rectification, both cycles are retained. Therefore, there is no power loss, or there is very little power loss in full-wave rectification as opposed to half-wave rectification. Next, we look at the second and the last way of doing full-wave rectification, which involves using 4 diodes, or what we call the bridge rectifier. So we are talking of 4 diodes because you can see we are using 4 diodes, that is the diodes D1, D2, D3, and D4. Now, during the first half cycle, point A is positive with respect to point C. So this one simply means that point A is positive, whereas point C is negative. So if point A is positive, it means that the current is going to flow from point A towards this direction. Therefore, this arrow represents the direction of current during the first half cycle. So the current flows from point A towards the diode D1, which of course is forward biased, then to point B, then of course through RL, then of course it will flow to point D, then through the diode D3, which is also forward biased, then to point C, then back to the starting point. Therefore, during the first half cycle, point A is positive with respect to point C, or point C is negative. Then the diodes D1 and D3 are forward biased, whereas the diodes D2 and D4 are reverse biased. For example, from point A, the current cannot move in this direction because you can see that D4 is actually reverse biased. Similarly, when the current moves from point A to point B, at this particular point, the current cannot follow this direction because D2 is reverse biased. Therefore, during the first half cycle, point A is positive with respect to point C, then diodes D1 and D3 are forward biased, whereas diodes D2 and D4 are reverse biased. Therefore, the current flows through the path, so it starts at point A, then it moves through the diode D1, which is forward biased, then to point B, then of course it moves through the RL, that is the resistor load. Then from there it moves through this direction to the point D. Then of course it moves through the diode D3, which is also forward biased, then of course to point C, then of course, which of course is negative in this particular case. At point C, it moves through this particular step down transformer, then of course it goes back to the starting point. So the path followed is A, diode D1, B, RL, then D, then diode D3, then C back to the starting point, which was point A. Now, during the second half cycle, point A now becomes negative with respect to point C. So that means point A becomes negative, whereas the point C becomes positive. Therefore, it means that the current is going to move from point C. So, that is during the second half cycle, point A becomes negative while point C becomes positive. Therefore, diodes D2 and D4 becomes forward biased. Remember, if point C is positive, the current will flow through the diode D2 because it is forward biased. It cannot go through D3 because if it tries moving in this direction, it finds that D3 is actually reverse biased. Therefore, the current will flow from point C through D2, which is forward biased, to point B. At point B, it cannot go through D1 because it is reverse biased. Therefore, it will be forced to move through RL, then of course through this particular direction here. Now, when it gets to point D, the current is going to move through diode D4, which is forward biased, then of course to point A, then of course back to the starting point, which was our point C. Therefore, this arrow, the second arrow, represents the direction of current during the second half cycle. So during the second half cycle, point A becomes negative with respect to point C, and D2 and D4 becomes forward biased, whereas diodes D1 and D3 becomes reverse biased. Therefore, the current flows through the path. So it starts at point C, it goes through D2, which is forward biased, then of course through point B, then of course it moves through the resistor load, then of course it moves through this particular point here, then it gets to point D. Once it gets to point D, it's going to move to the diode D4, then of course back to point A, which is negative in the second half cycle. Then of course it moves back through our step down transformer, which has fewer number of turns in the secondary coil as opposed to the primary coil. Then of course it goes back to the starting point, which was the point C, which is now positive in the second half cycle. Therefore, the path followed is C, diode D2, B, RL, D, D4, A, then of course back to the point C. Now, during both half cycles, current flows through the load resistor, that is RL, in the same direction. So the current flows through this particular direction, of course, which is the clockwise direction as it passes through RL. Now, advantages of a bridge rectifier, or what we are calling a 4-diode rectifier over 2-diode rectifier, is that one, a small transformer can be used because there is no need for center tapping. Remember, center tapping is the one that usually needs a larger transformer. Then the other advantage is that it is suitable for high voltage regulation. It can regulate very huge amounts of voltage because of course we are using a step down transformer in this particular case. So regardless of the large voltage from the alternating current source, it will be stepped down to smaller amounts of voltage. Then when a capacitor is connected to the output that is across the RL, that is our load resistor, it produces a smooth wave. So the purpose of the capacitor is to smoothen the output rectified voltage or the wave. Therefore, this will be the output voltage when we connect a capacitor through the RL or our load resistor. Therefore, you can be asked to state the purpose of the capacitor in rectification. It is simply used to smoothen the output rectified wave, or it is used to smoothen the output voltage. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that take the risk or lose the chance. So the quote is encouraging us to utilize the opportunities we get in life well so that we avoid regretting in future. Remember that Small opportunities often lead to great enterprises when well utilized. And lastly, recall that lucky people get opportunities. Brave people create opportunities, while winners convert problems into opportunities. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. This was our last lesson of physics and high school physics. Thank you very much for accompanying me through this particular whole journey. It has not been easy. Thank you for the encouraging comments. So that means in our next lesson, we'll be totally focusing on mathematics and physics practicals. Until next time, this is Kind Tuition Academy. Thank you very much.